Here are some of our goals for the day. 1, by the end of the day, I want you to recognize that the vertical and horizontal components of a projectile's motion act independently of one another. They do not affect one another, which is essentially what Omri was talking about earlier. 2, I want you to recognize that for a projectile, acceleration is only happening in the vertical direction due to gravity. And 3, you should be able to solve problems with projectile motion. That's the goal of today. Let's see how we can figure that out. First, we need to know what a projectile is. Okay? What a projectile is. And in physics, we define a projectile as an object that has been launched through the air that is no longer being propelled after it has been launched. Okay? The only force acting on it is gravity after release. That is a projectile. So by this definition, is a bird, Sam, a projectile? No. Is an airplane a projectile? No. Is a rocket a projectile? No. Is a baseball a projectile after you've hit it? Yes. Is a football a projectile after you've thrown it? Yes. Is a airplane a projectile whose engines have died? Yes. Okay, but it's kind of unusual because it's got wings and it messes things up. But so a projectile is not propelling itself through the air. Okay, that's our definition. A torpedo would not be a projectile because all right. Okay, some more vocabulary you need to know. Trajectory is a good fancy word. Trajectory just simply means the path that a projectile takes after it has been launched. Those of you that have taken math will start to recognize as we study projectiles that the projectile, if you launch a projectile at an angle rather than horizontally, it will take a path that is perfectly parabolic if you take away air resistance. Okay? So if you study parabolas in math and you understand the mathematical concepts to describe parabolic motion, it is something that actually does occur in nature. Projectiles follow parabolic path. Oh yeah, excellent. That's perfect. Okay? Range is another word that you're going to hear a lot, and range is the the horizontal distance that a projectile travels. That is called the range. And so the lab you were doing earlier, you were trying to see how the speed of the projectile affects its range if you launch it horizontally, and it seems that most of you came to the conclusion that the greater the horizontal velocity, the greater the range. All right. The key concept with projectiles, there's one key concept you must understand, and it is this. It has to do with the velocity of a projectile. The most important thing to remember is that the horizontal and the vertical velocities act independent of one another. You can change one, and it does not affect the other one, okay? So if you think about the experiment you did at the beginning, you changed the horizontal velocity of that marble, and it didn't change the time it was in the air, because that's vertical. The time it was in the air was the time it takes to fall, and it would have been exactly the same if you had dropped the marble or if you'd launched it at whatever speed. It's always going to be the same time because its vertical motion is independent of its horizontal motion. Okay? The higher table would affect the time, yes, but on a given from a given height, the horizontal velocity would not affect it. Okay? The horizontal velocity of a projectile is constant, assuming no air resistance. Why would that be? Why would it be constant horizontally? Since there are no horizontal forces, a projectile's horizontal velocity will be constant. However, there are forces vertically. What acts vertically? Gravity. So a projectile's motion vertically will accelerate, and it'll accelerate at negative 9.8 meters per second squared. So when we analyze projectile motion, we'll break it into pieces, and we'll do constant velocity in the horizontal direction. We'll do accelerated motion in the vertical direction, and everything's hunky-dory and it all works out. Okay? If you want to know how fast a projectile is moving at any given instant, at a given point in time, you basically add the two vectors. You add the horizontal velocity and the vertical velocity, and the resultant at that moment is the velocity of the projectile at that instant. Okay? Okay, yes. So let's look at some pictures to explain what this looks like a little bit more. If you are a visual learner, this is what we're talking about. This is what you just did. Here's our little red marble of science. We roll it off the table. We roll it off the table horizontally. It has a certain horizontal velocity when it leaves the table. Notice that that horizontal velocity stays constant. It does not change throughout the flight of the marble. The thing that changes is its vertical velocity. It increases because of gravity just exactly the same as if I would have dropped the marble. Okay? The vertical and the horizontal are independent of one another. So launching something horizontally, its vertical motion is exactly the same as if I dropped it. So the time is determined by how high it falls and nothing else. Okay? So technically, that lab that you guys just did where you rolled the marbles off the table, if the time was constant, finally, if you want to know the velocity of that object at any given instant, if you want to know how fast it's moving at a given instant, you just add up the vectors. Notice here I have a, let's get rid of all these drawings for a second. Can't do that when I'm holding the pen. Go away. Okay. So if I look at the horizontal velocity and I add the vertical velocity to it, it gives me the instantaneous velocity. And I can do that anywhere, right? Here I can add the horizontal and the vertical. I get the instantaneous. Or up here, same thing. Okay, so the instantaneous velocity is just the vector, the resultant of the horizontal and vertical velocities. This is a drawing of it. Let's look at an actual photograph of it. This is a picture taken of a marble that was launched horizontally, and it was taken with a strobe flash. So the strobe light flashed at constant time intervals. So we get a little dot where the marble is at constant time intervals. And if you'll notice that the horizontal velocity stayed constant throughout its path. The distance it traveled horizontally stayed constant for the same time interval, which tells me the velocity stays constant. However, the vertical velocity is increasing as would be expected.
Is that out of one of those fancy marble shooters?
Probably out of one of those fancy marble shooters. Okay. Now, this begs the question, and you guys have already thought through this pretty well. So here's the story you hear all the time. You have a gun, okay? You aim the gun horizontally, not up and in the air, but horizontally. And I shoot that gun, and I shoot that bullet horizontally. At the same time that I shoot it, if I were to drop the bullet, drop a bullet and shoot a bullet, which one would hit the ground first? Same time, okay? Same time, right? So I want to do it too. Okay, so we just saw the video where the drop bullet and the shot bullet hit at the same time. Now let's do some math. Let's try to figure out how we can calculate projectile motion, okay? Notice the scenario we've drawn here on the board. You're driving your car off of a cliff at 4 meters per second, okay? You happen to be leaving the cliff horizontally. The cliff is very tall, 200 meters high. Notice that at the bottom of the cliff, there are really sharp rocks that extend out about 25 meters, okay? If your car lands on those rocks, not only do you get crushed, you get exploded and die in a fiery, horrible death. It's miserable, okay? However, just 25 meters away from the cliff is a gigantic, happy, soft pillow of science, okay? And if your car lands on the pillow, life's good, and you live, okay? Now, okay, so what do? First thing we want to know, and this, again, this is a projectile that's launched horizontally. The first thing we want to know is how long you will be in the air. And what determines how long you'll be in the air? The height of the cliff. Excellent. The height, I knew that's what you're talking about. The height of the cliff. Does it matter how fast you're driving off the cliff? No, just like the experiment this morning. It does not matter how fast you're driving off the cliff. The height will determine how long you're in the air. Will you be accelerating vertically? Yes, you'll be accelerating vertically. Is there an equation that you remember that deals with distance, acceleration, and time? Omri. Okay. S equals ut plus 1/2 at squared. Beautiful. Okay, so what are we going to put in here for distance? 200, because we're talking about vertical motion right now. So 200, what's our initial velocity? 4. Is that true in this case? Because we're dealing with vertical motion. 0. Our initial vertical velocity is 0. So we're not dealing with horizontal. We're dealing with vertical right now, okay? So forget about this part, because it goes away, because our initial vertical velocity is 0. Then we have 1/2, 9.8 t squared. Let's solve that for t and see what we get. And anybody else get the same answer? Okay. So let's go to the next step. Let's talk about this one first. So the time we're in the air is 6.4 seconds. That's a huge amount of time, but remember a 200-meter cliff is also a huge cliff. So that makes sense, okay? Now, to figure out how far you're going to land from the cliff, we're dealing with horizontal distance, what we call range. And what's true about the velocity of a projectile horizontally? It's constant. And what equation do we deal with that deals with distance and time and velocity that's constant? Omer. Very simple. We just say distance equals velocity times time. However, in this case, we're dealing with the horizontal distance, so let's specify that we're talking about the horizontal velocity. Okay, what's our horizontal velocity? 4. And what's our time in the air? 6.39. And what do you get for our distance? 25.56 meters. And we've survived. We've hit the happy pillow, and life's good. Okay, awesome. So let's review what we did with horizontal projectiles. Okay, 1. First, you want to find the time it's in the air using distance equals 1/2 AT squared. It's important when you're using distance equals 1/2 AT squared, since we're talking about acceleration, that you are dealing with vertical motion, okay? And it's the vertical distance that determines the time the projectile will be in the air. This is only for projectiles that are launched horizontally. Secondly, we can find the range using distance equals VT, and we may use that equation because the horizontal velocity is constant. So we can use that equation that works really well with constant velocity. Please recognize that you just did a problem where you knew the height of the cliff and you knew the initial velocity. But sometimes you'll be given a problem that says, hey, if I drive off of a cliff at 4 meters per second and I land 25.2 meters away from the base, how high was the cliff? Does that make sense? It could be worded that way. Or if I drive off of a cliff and I'm in the air for 3 seconds and I land 15 meters away, how fast was I moving when I left the cliff? Those are other possibilities for how to do these problems. And the trick is always to break it down into horizontal and vertical components and deal with those independently, remembering that vertical is accelerated motion and horizontal is constant velocity. Now, we don't often launch our projectiles horizontally. This is a simplified scenario. In reality, if you're going to launch a projectile, you would like to launch it at an angle, right? Okay? If you're trying to launch a missile at your enemy in the next country over, and you launch it horizontally 6 feet off the ground, there's going to be a lot of people that have to duck when the missile comes through town, right? You don't do that. You aim it up in the air so it goes up and comes down on someone else, right? Or you're trying to hit a home run in baseball. You're not going to hit it horizontally and hope that it goes over the back wall. You're going to hit it up and try to get it up and over. So angled projectiles are the way to go. The situation's exactly the same, okay? For a projectile launched at an angle, the situation's the same. The horizontal and vertical components are still independent of one another. What we will do is we will take the initial velocity, that initial velocity, whatever the speed is at whatever angle, and we will break that vector into its x and y components. What we really want to know about projectiles is how fast it was moving horizontally at first and how fast it was moving vertically at first. Because as it flies through the air, notice that the horizontal velocity never changes. And the vertical velocity does change according to gravity, exactly the same as if we took something and threw it straight up in the air with this initial vertical velocity. It's exactly the same. At the top of its path, how much vertical velocity does it have? 0. And so how is it moving? It's just moving horizontally. For that instant, it's just moving sideways. It's not going up, it's not going down. The upward motion is always slowing down on the way up, and then it stops vertically, and then it comes back down and accelerates. Only for an instant, a very short moment in time. Yes. So let's try this process now. It's going to be very similar to the last process. The main different step is that first we're going to have to find out the horizontal and vertical components. And to do this, we're going to go and think about the X Games for a little bit, because we have the X Games, right? X Games come here every winter. All these guys come to town. It's often crazy. There's like half pipe and slope style and snowmobiles doing crazy things. Personally, I think the X Games are lacking a little bit. I don't think they have enough excitement, enough adrenaline. There's not enough really cool stuff going on. And so I thought of this new event. And this new event is awesome, and I submit it every year, and every year they come back and they're like, we're just not ready for it yet. But personally, I think it would really put the X Games over the top. And here's my event, okay? And this this is what the X Games really need, I think. And here's how it works, okay? You get a 22-meter shark tank, okay? And you fill it with very hungry sharks, and you don't feed them for a while, okay? And so there's these hungry sharks that are waiting to eat. In the middle, you put a flame that is 5 meters high. And this is no regular flame. This is like super intense, high temperature flame that if you touch it, yeah, you'll just die, okay? Then here's what you do. You put the contestants at the top, and you put them all together. This is like border cross or ski across, right? They all go at once. And there's 4 jumps, okay, all at different angles. One's at 30 degrees, one's at 40 degrees, one's at 50 degrees, and one's at 60 degrees, okay? And they have to decide which one they're going to hit. Now, you've set it up so that their skis and snowboards are the same, so they all hit the ramp at exactly the same speed, 15 meters per second, okay, is how fast they're going when they leave. They've got 4 choices, so they're kind of competing for which ramp are they going to try to hit. And here's what I love about this. Here's what I imagine. See, you also like douse them in gasoline so that if they touch the flames, boom, they just go up and you get a great show, okay? And also, you've put like blood in the tank so the sharks are like feeding frenzy, and so like if they hit the water, boom, they get eaten. It's just like, oh, it's serious, okay? This is serious stuff. And here's what I imagine. This is my favorite part. Like, all the guys are sitting up there. You can totally imagine this, right? All the guys are sitting at this X Games, right? So they got their big old baggy pants. They got their headphones on and their bandanas, and they're like, hurrah, dude, man, this is so cool. This is rad. And then one of the guys reaches in his jacket. I can totally watch. Reaches in his jacket, pulls out a calculator. And all the other guys are like, dude, you're such a dork. And he's like, yeah, I'm a dork, but I got a calculator. And he starts doing all this stuff, and I'm not going to die. And all the other guys with the headphones and the baggy pants are going to get eaten by sharks. Not that I'm biased or anything, but I think dorks should rule. Okay? Anyway, yeah, here's how it goes. Here's how it goes. So here's what we have to do. First of all, before we figure this out, if you were in this competition, let's think about which ramp you would hit, okay? We'll just kind of guess first, and then we'll calculate and see which one you should hit. How many of you would aim for the 30-degree ramp? 30, 40, 50, and 60, and you're all leaving at 15 meters per second. You all have the same velocity when you leave, or the same speed, you're just hitting different ramps, okay? So how many of you would aim for the 30-degree ramp? No? Yeah, no calculators, Omer. Not yet. 30? Okay, one of you for 30. How many of you are going for the 40-degree ramp? 1, 2, 3, 4, 5, 6, 7, 8 of you. How many of you are going for the 50-degree ramp? 1, 2, 3, 4, 5, 6, 7. 7 and 60? 1, 2, 3. Okay. Excellent. Let's now do the math and see what happens. Okay? Let's do the math and see what happens. Okay. Okay. The first thing we have to do, you guys, is to find the horizontal and the vertical velocities. And if you think about it, this is just vectors. This is what we've been doing. So here's your initial vector, 15. I'm going to call that just my initial velocity. Here's the angle that you're being launched at. These are basically projectiles. And really what I want to know is what is your x velocity and what is your y velocity when you leave the ramp. How can I figure that out? Omer.
If you set 15 to the magnitude of this angle. Oh, sorry. You already did that. You change beta to 1 degrees out of 40 and you solve for the sine or the cosine.
Sine or cosine. So we're going to use trigonometry. Excellent. Let's look at the horizontal first. Am I going to use sine or cosine? The horizontal will be cosine. How do you know that? Because of SOHCAHTOA, adjacent and hypotenuse. So the cosine of my angle equals the adjacent over the hypotenuse. I can rearrange this to say, hey, if I take my hypotenuse, which is my velocity, times the cosine of my angle, that will tell me my x component. I could do the same thing, except for using sine, and that will tell me my y component. You with me so far? Let's try it for 30, 40, 50, and 60. Who wants to do 30? Who wants to do 30? Tati. Okay, 30. You guys both do 30. You'll double check each other. 40. 40 over here. 50. You guys do 50 over here. Some of you. 60. Someone do 60. 60. Excellent. And if you didn't get a choice, just pick an angle and try this. That the angle. So it appears that the x and y's flip. And what's true about the angles where the x and y's flip? What does 30 and 60 add up to? And what does 40 and 50 add up to? So they're complementary. Complementary angles, the x and y components will flip. And if you actually think about the trig, it makes sense. Because check this out. Here's a right triangle, right? If this is 30, then this is 60. And if I use cosine to find that for 30, then that's going to be the sine of 60. And so they'll be inverse of one another that way. Okay? So now we've broken the initial velocity into its x and y components. The piece of information that will help us is knowing how long it's in the air, right? How long it's in the air. And in order to do that, you need to think about what's going on with the projectile for a second. So here's a projectile, okay? And if the projectile lands at the same height that it was launched, that makes our lives easier. Notice that its initial y velocity is here. What will its final y velocity be? The same but going down. Just like if I threw something straight up in the air, when I catch it again, it has the same velocity in the opposite direction. Excellent, okay? So this is going to help us figure out how long it's in the air. It'll be in the air for the exact same amount of time as if I took an object and threw it straight up in the air with that initial vertical velocity and let it come back down. If I could time that, it would be the same as this projectile. What's the equation? What was our first definition of acceleration mathematically? Definition of acceleration. Excellent. So the acceleration of an object is change in velocity over change in time. We'd like to know time. Can you figure out its change in y velocity? What would that be? Let's say for this first one, it starts off with 7.5 up. It ends up with 7.5 down. What's the change in velocity? 15 or 0 are the two answers I usually hear. Which one is it, 15 or 0? You go from plus 7.5 to negative 7.5. How much have you changed? 15. You've changed 15, okay? If you added them up, you get 0. But the difference between the two is 15. Because one's positive, one's negative, and you're going through 0, so 15 change. That make sense? Okay. And what's the acceleration in this situation? 9.8. So basically, if I take the acceleration of gravity and I double my initial y velocity, that equals the change in y velocity. That should tell me the time if I rearrange this. The time is equal to double the y velocity over g. Now, this doubling the y velocity thing only works when the landing is at the same height as the launching, okay? If I land at a different height, it gets more complicated. So let's calculate this for 30, 40, 50, and 60, the time that this projectile will be in the air using this equation. So we've just calculated the time each of these people will be in the air. Does it make sense that if the ramp is steeper, you will spend more time in the air? And that appears to be what we've gotten there, so that's good. Okay, now that we know how long you're in the air, what we'd also like to know is how far you travel, your range. How are we going to calculate the range? And why are you able to use that equation? Constant velocities. And what velocity are we going to use in this case? The horizontal velocity. Because that's what you're looking at now is the horizontal distance. And since that horizontal velocity is constant, we can take that horizontal velocity times the time you're in the air, and that will tell you how far you've traveled downstream or downrange. So let's do that. Calculate it. Tell me what you get. So we'll figure that out. We can figure that out. But first thing I want you to see, here's the ranges of the three. Notice that the person that hits the 30-degree ramp, yes, they're going to get eaten by sharks. The person that hits the 60-degree ramp, yes, they're going to get eaten by sharks. But now the critical question is, will they be cooked and eaten, or will they be eaten raw? You know, we don't know. We'll figure that out. So, two, something else to consider. And hopefully you notice this. Notice that the range of the 30 is exactly the same as the range of the 60. and the range of the 40 was the same as the range of the 50. The trajectories won't be the same, but the range will be. And if we were to visualize it, it would look something like this. It's kind of a cool thing about projectiles. The x and y were inverse for those complementary angles, and the range is the same for complementary angles. So if I launch a projectile at 10 degrees, it goes about that far. And if I launch it at 80 degrees, it goes the same farness. Okay? If I launch it at 30 degrees, it goes exactly the same as 60 degrees. And 45 degrees goes exactly the same as 45 degrees. Okay? 45 will get you the maximum range if air resistance is not taken into account. So now we already know that 2 of the ramps have caused an untimely end because of shark edibility. What we'd like to know now is who got burned by the flame. So we need to know maximum height. Okay? And maximum height what is it about a projectile launched at an angle that determines its maximum height? There are a variety of ways to determine maximum height. I have my own favorite, which I will share with you, but there are other ways you could do this. Here's what I would do. Let's think about what the projectile is doing. It's got a certain amount of time in the air. At what point in terms of the time of flight will it reach maximum height?
When the velocity...
In terms of time, halfway through, right? Halfway through the flight, it's at its maximum height. So if I take half of my total time and think about if I were to drop something that was falling for that time period, that will be my maximum height. It's kind of the same idea. If I were to drop something and it were to fall for that time, that would be exactly the same as if I threw something up in the air for that time, which is basically what my projectile is doing, okay? So if I take this equation again, distance equals 1/2 at squared, and I use half of the total time for t, and use gravity for the acceleration of gravity for a, that will give me my maximum height. Does that make sense? Kind of why that works? Okay. D would be your maximum height in this case if I use half the total time. Assuming, again, this is all assuming that the projectile lands at the same height that I launched it. It gets much more complicated when it lands at a different height. It's still doable, but this is all for same height, landing and launching, okay? Yep. So let's figure this out for 30, 40, 50, and 60. Okay, there's the times. Let's see what we get for 30, 40, 50, and 60.
I'm assuming you shouldn't use negative gravity.
You cleared the flames. Yes, we'll go back to the picture. But so here's what we get for maximum height. But think about one more way you could do maximum height if you wanted to. The other way you could do maximum height that I can think of is recognizing that you have an initial vertical velocity when you're launched. What's your vertical velocity at the top? With that information and the acceleration of gravity, you could also find by using this equation. Initial velocity squared, or final velocity squared equals initial velocity squared plus 2AD. Your initial velocity being whatever your initial y is, your final velocity being 0, because that's what you're, at the maximum height, that's what your y is. And then solving that for d would also give you maximum height. That's the other way of doing it if you want to. And both of those are totally valid. So now let's go back to our gruesome X game competition. And, you know, I apologize if I'm being kind of grisly, but it is almost Halloween. And let's visualize this for a second. So the competitors that hit the 30-degree ramp, they come down, they're going excited, they're going fast, and they catch on fire, boom, and then they get eaten by sharks. Oh, horrible, horrible. Okay. The 40-degree ramp, they go. Did they clear the flames? Yeah. They didn't clear. So they go, wah, they catch on fire, and then they land on the other side, just charred like a marshmallow. Horrible, horrible. Okay, okay. The 50-degree people, wahoo! They clear. They do a flip just for fun, and yes, they land. Woo! And life's good. Okay, and then the 60-degree people catch big air. They do like a McTwisty Nuffin and McMuffin, and they land and get eaten by sharks. That's horrible. Okay. Poor shark. Shark gets cooked food. Shark has a choice between cooked food and raw. It's a donut-shaped pool, though, so they can swim around. Okay. Yes. No, remember it was intense flames of death. It was horrible. Yeah. So, yes, Sky. Okay, so let's run through kind of the steps to projectiles launched at an angle. The first thing you want to do is find the x and y components of the initial velocity, okay, using those trig formulas. Again, I don't think these formulas are in your packet. It's just, but you do have a section in your packet about how to break a vector into its x and y components. So hopefully you know how to do that. You're breaking it into x and y components. Once you've done that, you would like to find how long the projectile is in the air, and you can use that equation to do that. The time it's in the air will equal its change in vertical velocity divided by the acceleration of gravity. Okay, that would be step number 2. Okay, so once you figure those things out, we can then find how far it goes. And again, horizontal motion is easy because it's just horizontal velocity times time. And once you've done that, if you would like to know how high it goes, you just use distance equals 1/2 AT squared, recognizing that you need to use half of the total time to find the maximum height. Okay. Feel free, if you want, to also do maximum height using this equation, making sure that you're using the y velocities. That would also work equally well, if you can think that one. And as we go back to our X Games shark problem, there's all the numbers that I got when I did it. So you can check that out, try it out, see how it works.